Okay, today we're going to start chapter 13. We're not going to get very far into chapter 13, and then you're going to have several days off because we're approaching Easter break. But I wanted to get started since we're already losing some valuable time due to all the disruptions and interruptions. So what we're going to go over today, I'm going to assign you some problems. Those do not have to be completed until the Tuesday after Easter. So it's up to you when you want to do those. Just sometime between now and then will be great. But we're going to start chapter 13, which is on the topic of thermodynamics. So as I pull up my information for you, here are your notes. I will post them to Google Classroom as well. They may not be word for word, so take notes as you watch the videos. But thermochemistry. Thermochemistry is thermodynamics in chemistry. So what does that mean? We talk about how energy gets transferred during chemical reactions, or even if it's not a chemical reaction, during phase changes. So how much energy gets transferred when a substance melts, or a substance evaporates, or a substance condenses, or a substance freezes. That also involves thermodynamics in chemistry, or thermochemistry, as we could also call it. The heat and temperature, what's the difference? All right, so if you measure the temperature of something, you are measuring how much energy the particles of that sample have. Okay. How much kinetic energy, so how much are they moving? That gives you your temperature reading. But heat is the total amount of thermal energy that gets transferred from one substance to another. So how much heat energy, thermal energy is heat energy, moves from one thing to another. And we're going to use joules or kilojoules as our unit when we talk about heat. So temperature, how much energy are in the substances that you're measuring, so the particles. So if something is a solid, meaning it's frozen, it has a lower temperature because there's less energy. Those molecules in a solid, doesn't matter if it's water or something else, those molecules or atoms are not moving very fast. They're moving very slow. They don't have much energy at all compared to their liquid forms. So that's why a solid when the substance is in its solid state, it has a lower temperature than when it's in its liquid state or in its gas state. Because as you know, as you go from solids to liquids to gases, the particles, whether it be atoms or molecules of that substance, start to pick up energy depending on the phase. So solid, very little energy. Those atoms or molecules aren't moving much at all. You go to liquid, they have a little more motion there, and then to the gas, they're bouncing all over the place. And so you can have a higher temperature at the gaseous state as compared to the solid state. Heat transfer, how much thermal energy goes from one substance to the next. That's what heat is. Okay. Now, there's a new term for you. We're going to talk about enthalpy. Enthalpy. And we're going to use the letter H as the abbreviation for enthalpy. And we're going to come back and forth between enthalpy and something called specific heat. But notice heat starts with an H, but that's not what we're talking about. We're talking about enthalpy. That is given the symbol H. Okay. Now that's defined as how much thermal energy a system has if the pressure is held constant. Okay. We use something called a calorimeter in order to measure enthalpy. We're going to talk about a calorimeter. I'm actually going to post a video that you have to watch as well that shows what calorimeters are. We would, and if we were at school, we would build a simple calorimeter and we would do a lab with that. Instead, I'm going to have you watch a video about simple calorimetry, okay? So basically a calorimeter is an insulated container, kind of like a thermos, but you would use, if we were doing this at school, we would use truly like a styrofoam coffee cup to make our calorimeter. That's obviously very simple, and then they get more sophisticated depending on what you're trying to do. All right, and then what you're going to do is as chemical reactions occur, doesn't matter what the chemical reaction is, Remember, chemical reaction is when one or two more things react together and they create something else. That chemical reaction either requires an input of energy, means it takes in energy in order to happen, or it gives off energy. Either situation would result in a temperature change. So a calorimeter uses a thermometer and measures the temperature change in that chemical reaction. Now I'm going to show you an image. This is what we call a bomb calorimeter. Now the reason it's called a bomb is because inside here, this chamber is where you put the things that you want to measure. So your reactants go in here and you watch and you allow the chemical reaction to occur. So this is where you put your reactants for the reaction chamber. If there needs to be an igniter, if something needs to happen in order to stimulate the reaction, you've got that there. And then you can come up here with the ignition wires that are going to be connected and make sure everything has enough input to get going. So whether that's an electrical source or some other source of energy to get the reaction going. Now, this is not a coffee cup calorimeter. That will be in the video. You'll see that example. This is a bomb calorimeter, hence the term the bomb, which is where the reaction will occur. We use this all the time. When you look at a food label and you see how many calories are in that amount of food, it has been tested in a calorimeter and it has been measured so that you know exactly how many calories you are consuming. Now, a little trick. What that really is kilocalories. So when you see that make it simple, when you see that a granola bar, let's say a small granola bar has 100 calories, a little secret for you. That really means 100 times 1,000. So 100,000 calories is what that really is. Because for whatever reason, we've chosen not to label it as kilocalories, even though what you're really eating is 100 kilocalories. The system we have in place just lists it as calories. Okay. Now, the way you measure the enthalpy, remember that's that H abbreviation. Enthalpy of the reaction is captured. So you have this bomb here, and then notice the label water. This right here, this line is the water line, and you'll notice your thermometer goes in and measures the temperature change of the water. And that water is going to either, depending on what's going on in this reaction chamber, it's that reaction is either going to give off heat, which would make this temperature go up, or it's actually going to absorb heat from the water and the temperature will go down. And you are going to, in order to figure out how much energy is being either absorbed or given off by this reaction, you're going to measure the temperature change of the water. Okay, that's how that calorimetry, this is how those calorimeters work. Even if it were just a simple bomb calorimeter, you would still be doing the same thing. You would still be measuring the change of the temperature of water that's surrounding whatever chemical reaction you have going on. Now, sometimes we don't have a chemical reaction. Sometimes it's just phase changes. So there are two types of heat when we talk about phase changes. You have something called sensible heat. All right, and we measure latent heat. Now, here's why. Sensible heat, actually, you notice when that means you're noticing a temperature change. Latent heat just produces the phase change. Now, during latent heat, latent means it's steady. So latent, when you're in the process of a phase change, your temperature of the substance does not change. So if you have a cup of water and you just sit it there, and if you were to put a thermometer in that cup of water and you just leave it on your kitchen counter and you come back and check it every 5 minutes, as long as there is still ice in that container and the ice is still in the process of melting, you would not get a temperature change. It would stay at 0 degrees Celsius until every drop, every piece of ice had completely melted. Then once all of that ice is gone, then you would start to see the temperature elevate. And eventually it would reach room temperature if you just leave it sitting on the counter long enough. And that might be a fun experiment for you to try if you have a thermometer at home that you could put in water and just let it sit. Now, most of us have digital thermometers now, and so that's not really possible. But if you did have like a normal old school type of thermometer at your house, I would recommend doing that experiment just so you would understand that's really what's happening. Your ice water stays at 0 degrees until all of the ice has completely melted. That's what's called latent heat. There's heat going into the system that's causing the ice to melt, but it is not causing an increase of temperature. It takes every bit of ice going into the liquid form before the temperature of your container, the liquid in your container, actually starts to rise. Okay, so sensible heat produces a temperature change. Latent heat does not. And I'm going to show you a graph. This graph is also in your book. Let me turn to the page, on page 337. So here's this is all dealing with water. Okay. Now notice you have thermal energy in joules here. Notice what happens. This is water. The freezing point of water, and the melting point actually, is 0 degrees Celsius. So what happens, notice that the temperature will rise from -20. It will rise to room temperature. So if there was some way you could get, take a piece of ice out of your freezer, you measured that, you could get a reading below 0, possibly, if your freezer had been cold enough. But depending on how cold your freezer is, you would notice a difference. But once that ice reaches 0, it's all going to be in the melting process, and there's no temperature change. Notice that line, that's a flat line. This is the temperature. So if it's steady here, it's absorbing energy. Notice the energy line is increasing, but the temperature is not. Now, here we get, at the end of this, all the ice is gone, and now we just have water. Now watch what happens. Ooh, all the way up. It doesn't have to gain much energy at all for all of that ice to melt. And then we let it warm up. Now look, it stops at 100 degrees though, if we're warming up that water. And what starts happening at 100 degrees? That's the boiling point of water. And we have a lot of water. So look, even though we're increasing the amount of energy, as long as there is still water and no gas, or excuse me, and there's still water and some gas, as long as there's water, that temperature does not rise above 0 degrees. And then at this point here, all of the water is gone and the gas can increase in temperature again. But as long as you have some water right here, as long as you have some water, you're not going to rise above 100 degrees. And as long as you have some ice, you're not going to rise above 0 degrees, even though there is an increase in energy. Okay, now we're going to talk a little bit about this enthalpy of fusion. And we're going to then we'll come back to this idea of enthalpy actually after Easter. So molar. Now notice, we're kind of done with the idea of molality, at least for a little while. And we're going back to the idea of molarity. So we're going to look at the molar, means we're going to be dealing with moles, enthalpy of fusion. Sometimes this is called heat of fusion. And that's normally probably what I'll be calling it, heat of fusion. Even though it's enthalpy, we use that H for enthalpy, we can call it heat of fusion. So what this means is the amount of energy required. Now fusion, okay, let's talk about that in a second. Just keep in mind the idea of the word fusion. That's the amount of energy required to melt, here we go, 1 mole of a solid to a liquid when no temperature change occurs. Okay, so how much energy is required to melt 1 mole of a solid? So like 1 mole of ice. How much energy is required to melt 1 mole of ice, for example, to water? In your units here are going to be kilojoules per mole. Now, interesting thing about this is the reason we're calling fusion, if you fuse something together, it kind of means it comes together, right? So the idea behind this is that the same amount of energy is released when 1 mole of liquid freezes. All right, so it's just going backwards. So the same amount of energy is required to melt 1 mole of ice to water as is released when 1 mole of water freezes to ice. Okay, so it's just kind of like the difference between a positive value and a negative value. So when you freeze something, you're going to release energy. When you melt something, that's going to require energy input. But for a substance, for any given substance, the heat of fusion, the value, you're going to require the same amount of energy input to melt it as is released when it freezes. So we talk about fusion, and then we're going to talk about vaporization, which means to convert it to a gas. So the enthalpy of vaporization is sometimes called the heat of vaporization, and it's similar, except this time we're talking about reaching the boiling point and letting it vaporize to gas. All right, so this idea is the quantity of energy required to convert 1 mole of a liquid at its boiling point. How do we get that liquid to a vapor? How much energy is required? And these are, again, these values, heat of vaporization and heat of fusion. You don't have to memorize those. They'll either be given to you when we start solving problems with them, or you can look them up. There's a table on page 13-1 on page 337 that has a few examples. There are many other substances, many other substances. Obviously, there are only 4 listed in that table, but they would be given to you. All right. Now, just a quick, hopefully a simple drawing to help you see how energy is required versus given off. So if you want to melt an ice cube, it makes sense that you'd have to put energy into it to get it to liquid form. But if you have a liquid, energy would have to be removed to go back to the solid form. Likewise, if you have water and you want to evaporate it, you're going to put energy into it. All right. If you need to get condensation and get back to liquid form, you're going to have to remove energy from that system. Study that for a few minutes and make sure that makes sense. If not, drop me a question. Okay. Now, the problems that we're going to do today, and we're going to wrap up here with a couple of examples of these problems. We're going to talk about the specific heat. We're going to come back to enthalpy later. That was just an introduction to enthalpy. We're going to talk, though, about the specific heat. Now, there's something called the specific heat, and it is defined as the amount of thermal energy required to raise the temperature of 1 gram of any substance by 1 degree Celsius. So how much energy is required to raise, let's take water, 1 gram of water by 1 degree Celsius? How much energy does it take to raise the temperature by 1 degree if you have 1 gram of a substance? And we're going to look at units of joules per gram. Okay. And then, what do you think this K stands for? Okay. That is my fault. I made a mistake. Okay. It should be degrees Celsius. I was thinking Kelvin. That's my mistake. All right. So joules per gram times degrees Celsius. Now, this is another one of those things where you're going to have specific heat charts. So I did not write this in your notes. I don't think it's on the next page. No, I did not. So the chart for specific heats is on page 338. And there's a whole lot of them listed. It's not an indefinite list, but it does have several, maybe 10 or so substances. And again, I will either refer you to a chart, or you will be given the information you need in the problem that you're going to solve. You don't have to memorize these. All right. So here's an equation that you're going to need to memorize. It's called the thermal energy input. Now look at the Q I've broken it down here for you, the thermal energy put into a system. M is the mass of the substance, whatever you're measuring. Specific heat is what you're going to look up in a table. And delta T is the change in temperature. And again, we're going to be dealing in degrees Celsius, not Kelvin. I apologize for that early mistake. Just have it. All right. So let's go here. let's look at a type of problem. So Q equals, and this is the way I always remembered it, and I finally, when I was in high school, you're gonna do enough of these problems that you're gonna memorize it. That every time you solve one of these thermal energy input problems, I want you to write the equation down. When you turn in your homework, that's gonna be due next, like in multiple days from now, the Tuesday after Easter, you need to write the formula for every problem, and it's Q equals MC delta T. Q equals MC delta T. Q equals MC delta T. Write it for every problem that I ask you to solve. Okay, I want to see that formula written, or I'm going to send it back to you and say, what formula did you use? Write it down. All right, now, so here's a general rule. Substances that have a higher specific heat value will retain heat for longer periods of time than those with low specific heats. Water is a great example of this. Think about summer at the pool. Okay. At the beginning of the summer, you have a lot of water in that pool. How cold is that water? It's cold. Even if on that first day of summer, if the pool is open and it's 90 degrees outside, that water is cold. That's because there's a lot of water in there that has to get heated up because you're taking into account the mass and water specific heat. Water has a very high specific heat capacity, meaning it takes a whole lot of energy to raise that water's temperature by 1 degree Celsius. A lot of energy. But once water heats up, it takes a whole lot of, it has to lose a lot of energy before, that temperature starts to drop. Why water stays warmer for longer. Okay, which is also why it can be freezing outside for periods of time, but it takes forever for like a river or a lake to freeze over because that specific heat capacity of water is extremely high. All right, the last thing I'm going to do is talk to you about two types of problems that you might see using Q equals MC delta T. MC delta T. Q equals MC delta T. I better see you write it down for every problem I assign you. Here's a type of a problem. If 942 joules of thermal energy are added to 50 grams of water at 25.1 degrees Celsius, what will its final temperature be? Now notice, the formula is a change in temperature. So you have to take that into account and use it to find a new temperature. Okay, so Q, that's our heat. Q. 904 energy of 942 joules equals mass 50 grams times the specific heat capacity of water, which is 4.18 joules per gram times degrees Celsius. Now, we're looking for temperature. So what we're going to solve for is the delta T. So I'm going to multiply 50 by 4.8 and divide all of that. Take 942 and divide 942 by all of that. That will give me my change in temperature. When you do that math, you should get 4.51 degrees Celsius. So now I go back to my original. The water was already at 25.1 degrees. So I'm going to take my delta T, add it to there to 25.1. And with sig figs and rounding, I get 29.6 degrees Celsius. So that will be the new temperature. So that was just 50 grams of water that was already at about room temperature, 25.1 degrees, a little warmer than room temperature, okay? Now, let's go to this. A 28 gram sample, let me superscript my 28 gram sample of silver is heated from 15 degrees Celsius to 85 degrees Celsius. How many joules were added to the sample? So Q is the heat. I'm looking at this, so I'm just going to have to solve for Q. Now, I know the mass, 28 grams. Mass is 28 grams. I would look up the specific heat capacity of silver, which is on page 338. And it's 0.23 joules per gram times degrees Celsius. But I would have to calculate delta T because I know that I'm heating it from 15 degrees to 85 degrees Celsius. So my delta T is 85 minus 15. That gives me 70 degrees Celsius. Okay. And that's just straightforward, 28 times 0.23, which I looked up, times 70, which I got by subtracting 85 minus 15. And that gives me about 450 joules. All right, check the problems that are going to be listed along with this video, and I will see you guys back here after Easter. I pray you have a wonderful holiday with your family, and I hope you all are well and healthy. I miss you.